It's a pleasure to be with you. Can you all hear me okay?
Yes.
Thank you. So I'll be speaking about some work I've done with Will Happer of Princeton. So as Jim mentioned, we're interested in studying how radiation from the surface of the Earth goes through the atmosphere, and also the atmosphere through its greenhouse gases also emits heat or infrared radiation. And this radiation eventually works its way to outer space. So a greenhouse gas just refers to a gas which transmits sunlight, visible radiation, but infrared radiation it absorbs. So we're looking at the effects of water vapor, carbon dioxide, ozone, nitrous oxide, and methane. Now, if we look at the concentrations of these gases in the atmosphere, there have been measurements taken at Mauna Loa, Hawaii for the last several decades, and they show that the concentrations of N2O has increased from about 300 parts per billion, in 1980 to about 330 parts per billion today. In the case of methane, it has also gone up quite substantially. I'll be saying a bit more of that about that in a minute or so. And carbon dioxide has gone up from a concentration of about 320 parts per million in 1960 to over 400 parts per million today. Now, the source of the increase of CO2 is the combustion of fossil fuels, oil, natural gas, and coal. And the reason why I say that so definitively is if you look at this plot, which shows the increase of CO2 versus time, sorry about that. There are certain periods where you see it slowing, and that inevitably coincides with an economic recession throughout the globe. So during a recession, there is less fossil fuel use. Secondly, if you look at the amount of CO2 produced, it correlates with a decrease in oxygen. So in the plot below, we see the concentration of CO2 as measured at Alert, Canada. Alert is the most northerly part of the Earth's landmass at about 80 degrees north in latitude. So the blue curve shows a steady increase of CO2 from 1991 to 2013. And this corresponds to a decrease in oxygen, as shown in red, from over the same period of time. Now, the oxygen decrease of 90 parts per million is larger than the CO2 increase of about 36 parts per million. And the reason is that some of the CO2 is taken up by plants that are growing, and also part of it is absorbed by the oceans. In case any of you are worried about the oxygen level going down, keep in mind oxygen is 20% of the atmosphere, or 200,000 parts per million. So a decrease of 90 ppm is negligible. The other part that you notice from the CO2 curve is there's this annual oscillation. And the reason for that is that plants suck CO2 out of the atmosphere, especially in the spring and summer. Most of the Earth's landmass is located in the northern hemisphere. So if you look at this picture in February, the CO2 concentration is quite a bit higher in the northern hemisphere when plants are decaying compared to at the end of the summer as measured in October. The little red dot here that you see in the right figure, that's the result of CO2 produced in a forest fire in Indonesia. Now, if you want to measure the concentrations of these greenhouse gases, say thousands of years ago, what people do is they go and get ice cores from either, say, Greenland or the Antarctic. So every year snow falls on these ice sheets. Eventually, these succeeding layers of snow compact the snow below, and this turns into ice. And trapped into this ice, you have bubbles. So these bubbles of gas can be tested, and you can then determine the concentration of CO2. In addition, you'd like to determine the temperature. And the way they determine temperature is by looking at the isotopic composition of, say, the water. Water normally consists of 2 hydrogen atoms and an oxygen atom. Sometimes instead of a hydrogen, there's a deuterium isotope. Deuterium is like a hydrogen atom with an extra neutron in the nucleus, so it's a little heavier. Sometimes instead of oxygen 16, you can have oxygen 18, which has 2 additional neutrons. So if you look at the heavy water composition in the snow or the ice layer, you can determine the temperature. And the reason is that a heavier water molecule takes a bit more energy to evaporate. So the determination of the concentration of this heavier isotope gives you the temperature. So that's how they determine that temperature shown in the plot below. And you see very quickly this correlation. If the temperature goes up, the CO2 goes up. If the temperature falls, the CO2 goes down, etc. So some people see these 2 graphs and they immediately say, oh, case closed. This is the smoking gun of the global warming theory. However, if you look at these graphs a bit more carefully, what you find is that first the temperature goes up, and only about 500 to 800 years later, only then does the CO2 increase. Why does the CO2 go up? Well, there's a lot of CO2 absorbed in the oceans. If you heat the ocean a little bit, more CO2 comes out into the atmosphere. So it's a bit like heating a pop bottle. When you heat a pop bottle, the bubbles of CO2 come out at the top. Next, I'd like to talk a little bit about methane. And on the right, you see the data from Mauna Loa. So red is the slight oscillations that we see because of the plant growth changing by seasons. And then the black curve is the average through a year of the red data. So we see an increase. However, what is a bit difficult to understand at first is during the 1990s, early 2000s, methane leveled off. In fact, in one of those years, methane actually decreased. And the obvious question to ask is why? I have not found a satisfactory answer. The only thing I have heard is that the Russians had some leaky pipelines and they adopted Western technology after communism fell, and therefore the leakage of natural gas or methane from the pipelines decreased, and that was responsible for the leveling off of methane. I'm a bit skeptical about that argument. Another possible source of methane would be, say, warming of the permafrost. There's a lot of methane trapped in there, so if the permafrost warms, you would expect methane to be released. However, in the 1990s, temperatures were going up, and it's precisely during that period when methane started to level off, or at least increase, slow down. So there isn't a satisfactory answer to the question, why did its increase slow down in the late 1990s, early 2000s? On the left, you see a bit of a longer time period. The black curve is the methane concentration. The red is the rate of change, or the derivative of the black curve. And you can again see in 1905, something funny happened. If you know your history, that's when the Tsar had some riots and he recalled the Russian parliament. But I'm skeptical about whether that had any effect on global methane. So methane concentration is not well understood. And if anyone finds a definitive paper on that, I'm very interested. Now, what we do in our work is we solve the so-called Schwarzschild equation. This describes how the intensity of the radiation at a frequency nu and an altitude z varies. And it depends on kappa, which is the absorption coefficient. Of course, this has to take into account the absorption due to these 5 greenhouse gases, H2O, CO2, ozone, methane, and N2O. And then on the right side, we also see the Planck brightness function, B. So this just depends on the temperature. So in the graph below, we see the Planck brightness evaluated for the Earth's average surface temperature of about 15 Celsius. So this is a function that is peaked at about 600 wave numbers. This is in the infrared. Now, if we were to have a very high temperature, like the sun, then of course we would see visible light produced by the Planck brightness function. So at the low temperature of the Earth's surface, those frequencies are in the infrared range. It's not something that a human can understand or see. Some cats apparently have some ability to see infrared light. So if your cat had perfect infrared vision, he or she would be able to see that blue intensity curve of the Planck brightness. The next thing we need to understand is what is the temperature profile of the atmosphere? At the surface of the Earth, the average temperature is about 15 Celsius. As you go up to about the Tropopause height at about 11 kilometers for mid-latitudes, the temperature is about 220 Kelvin. It remains stable to about 20 kilometers, and thereafter it begins to increase. And the reason is you have ozone. Ozone absorbs ultraviolet light from the sun, and this causes the upper stratosphere to warm. When you get to very high altitudes above 50 kilometers, the atmosphere thins out and the temperature drops. Next, we look at the observed concentrations of our greenhouse gases. It turns out that observations show that the CO2 concentration remains 400 parts per million no matter what altitude you are at. That is not the case for these other greenhouse gases. For example, water vapor, when you go up in altitude, the temperature falls and the water vapor decreases very sharply. Ozone, it has a maximum shown in that brown curve at about an altitude of 35 kilometers. The nitrous oxide curve in the green and the dashed black curve for methane show also a slight variation of the concentration of those gases with altitude. So it's the temperature dependence, the concentration dependence on altitude that we consider in our work. Next, we want to know what are all the possible transitions or infrared colors at which these molecules absorb. And that we show here in this graph. In the upper graph, we consider water vapor. So each blue dot is a transition that we consider. There obviously are thousands, tens of thousands of these little blue dots and red dots, etc. The black curve is the Planck function evaluated at the surface temperature. For CO2, you see that the peak of this black curve coincides with a lot of these red dots. So CO2 has transitions where the Planck function has a maximum, and that's why CO2 is an important greenhouse gas. And etc. You see ozone, N2O, and methane having a lot of frequencies we consider. So when you put that into the program, you can calculate the heat flux. This is the power per square meter coming out at the top of the atmosphere. Your top of the atmosphere means a height of about 86 kilometers. So in the upper graph, you see this blue curve, and that is the curve that you would get if you have a transparent atmosphere with no greenhouse gases. Next, we put in our water vapor, our ozone, our methane, our N2O, but no CO2. And then you get this green curve. At first, you may not see the green curve because it's superimposed, by the black. So green means no CO2. Black means 400 parts per million CO2, which is about the present concentration of CO2. And red means doubling the CO2 concentration to 800 parts per million. So you see there's this dramatic effect at around 666 wave numbers, which is the effect of CO2 right here. You also see another peak, dip in this curve around 1,050 wave numbers. That's due to ozone. From about 1,200 on, this is mainly effect of water vapor. I've listed N2O methane, though they are quite small. So it's the difference between the red and the black curve that all of the global warming fuss is about. Now below, we do the same thing, but now we do it by varying the concentration of N2O. I'm trying to get my cursor, there it is. So the blue again is for a transparent atmosphere having no greenhouse gases. Black means our standard atmosphere where we have our water vapor, CO2, N2O, methane, ozone. And now green means we take out all our N2O. Red means we double our N2O. And the difference between the black and the red curve show you the global warming effects due to doubling N2O. And you see there's just a very tiny bit evident around 1,250 wave numbers. Now I could show you the same graph where we changed the concentration of methane. I think I discussed that in a prior talk to ICSF, which I believe is available at the ICSF website. Now you're probably saying, why should I pay attention to you? How do you know you've done things correctly? And the way a scientist does that is they look at observations and then they see if their computations agree with what's observed. On the top three graphs here, we look at data measured by a satellite that looks at radiation coming out of the atmosphere above the Sahara, then the Mediterranean and Antarctica. And on the left side is our computations. And if you look for the Sahara, you see that the vertical scale, this is intensity, goes from 0 to 200. The red curve, that's the Planck curve for a temperature of about 320 Kelvin or about 45 degrees Celsius. So the surface of the Sahara is hot. Now, if you go to the Mediterranean, the intensity axis just goes from 0 to 150. The Mediterranean is cooler, so you get less intensity produced. So we see the Sahara calculations for the model agree very nicely with those of the observations, and the same is true for the Mediterranean. For Antarctica, it gets rather interesting. The red curve is below our observation, the black. And the reason for that is that the surface of the Antarctica is colder than the air about a kilometer higher. This is known as a temperature inversion. So the intensity that the satellite sees is greater than if you just saw the intensity due to a cold surface. So we like the agreement between the model and the observations very much. Now, in the last year or so, we have also looked at downwelling. So if we put the instrument now at the surface of the Earth and have it look up, you can look at the radiation that is produced, detected. And we have looked at observations taken at Nauru. This is a place in the Western Pacific in the tropics, and we do quite well. We've also looked at Point Barrow, Alaska. And again, there's nice agreement between the model and the observations. Now, one thing that I should point out is that when we look at the Nauru and Point Barrow, Alaska observations and go to fit them or calculate what they should be like in the model, we use a fudge factor called the water continuum. And I say fudge factor is because people don't know what this water continuum is. Some people believe it's a water dimer, 2 water molecules stuck together, or even a water trimer, 3 water molecules stuck together. We don't know. So when we put in that, what people think that effect is of this water continuum, that's how we got that nice agreement between the model and the observations. And the reason we don't like it is we really want to understand what we're doing. You can also ask, why isn't the water continuum important for modeling the Sahara, Mediterranean, and Antarctica satellite observations? And it turns out most water is close to the Earth's surface. When you get higher in the atmosphere, it's very small. So we have looked at the effects of the continuum, and they affect the top of the atmosphere observations by less than 1%. So it's completely needless to consider it there. Now, if you integrate the flux at all the different frequencies, then we get this plot on the left of this figure. So here the horizontal axis is flux, and the vertical axis is the altitude from 0 to 86 kilometers. So green is the standard atmosphere where we have 400 parts per million CO2. Red is the effect of doubling CO2 to 800 parts per million. And if you look carefully, there's a slight shift of this green curve to the left. Now, the solar intensity, which heats the Earth, is constant. So if less radiation is emitted because we double CO2, in the long run, we're going to get some heating of the atmosphere. So this is then going to cause heating, and that heating is proportional to the difference between the red and the green curve. And this is what's known as the forcing. So the forcing is the flux when you have 400 parts per million CO2 minus the flux at double CO2. And this is 3 watts per square meter at the top of the atmosphere. Now, we've compared that to what others have found. There's a review paper by Collins, and other people have got about 2.8 watts per square meter. For nitrous oxide, if we double it, we get 1.1. Others have gotten 1.2. Methane, we also agree quite well with other people. Ozone, we are not aware of others who have calculated. For water vapor, there is a difference. We get 0.7 watts per square meter. Collins get 1.1, and this is for a 6% increase of H2O. Why not double hydrogen, water vapor? Well, then you get greater than 100% relative humidity. So 6% increase in H2O. This corresponds to the increase of water vapor that you get, or the increase of the saturation water vapor that you get if you increase the temperature by 1 degree centigrade. Next, I'd like to talk about something called saturation. So here we have plotted the flux versus various levels of the CO2. Once again, green is the 0 parts per million CO2. Then we go to 50 parts per million CO2, 100, all the way up to 800. And you see the only difference, sorry for that, is in this region around 666 wave numbers. And it isn't so dramatic when an change when you double CO2. And this is what's called saturation. So it's been known for over a century that the increase in surface temperature is proportional to the logarithm of the CO2 concentration at time t divided by C naught at this earlier time. Now, this is a logarithm with respect to base 2, and you multiply it by S, and S is called the climate sensitivity. Now, Arrhenius, he estimated a climate sensitivity of about 2 to 5.5 degrees Celsius. We estimate 1.4 to about 2.3 Celsius. Now, let me explain that. First of all, if you had the atmosphere increase in temperature at all points in the atmosphere, at all altitudes by the same height, then you would get a temperature increase of about 1 degree centigrade. Everyone agrees with it. However, when you double the CO2, In the stratosphere, you can think of having a bigger radiator. If you have a bigger radiator, you get cooling. So the effect of doubling CO2 is you're going to be cooling the stratosphere. And that means to get the same amount of heat out at the top of the atmosphere, the lower part of the atmosphere in the troposphere has to warm more than it otherwise would. So that's how you get a warming of 1.4 at the surface. Next, where does the 2.3 comes from? Well, that comes from the so-called feedback effect of water vapor. If you increase the temperature, you would expect there to be more water vapor in the atmosphere. If the relative humidity remains constant at all altitudes, then you can expect the temperature at the surface to go up to about 2.3 Celsius. Now, the question, is that observed? And the answer is no, it isn't. So probably the increase in temperature is more likely to be closer to 1.4 than 2.3. Now, the IPCC, they have come up with a bunch of climate models. I'll be speaking about that later. But they come up with a climate sensitivity in the range of 2.5 to 4. The most recent IPCC report says the best answer is probably about 3 Celsius. Now, so far, all we have discussed is clear skies. What happens when you have clouds? And if you look at a picture of the Earth, about 2/3 of the Earth is covered by clouds at any one time. So this is an important question to ask. Well, here's some more data from that satellite looking at the Western Pacific, the tropics. And the upper curve, this is for the case of a clear sky. And we can model that in the lower left. We can double the CO2 level. The data was taken in the early 70s, so that's CO2 concentration was about 326 parts per million. Doubling it gives you a CO2 concentration of 652 parts per million. And if you take the difference between the red and the black curve, you get a positive forcing of 3.15 watts per square meter. This is a bit larger than the 3 watts per square meter I talked about earlier because this is a tropical region, so the temperature profile is a little different than it is for a mid-latitude region we considered earlier. So a positive forcing means that you get a warming of the Earth's surface. Now, if you look at the satellite observations, we also have data taken when there is a lot of clouds over the Western Pacific. So you just see this little bump at 666, that's the CO2, and also a little bump corresponding to ozone. And this we have modeled on the right. Again, we have doubled the CO2, and this little curve here you probably can't see, so we've blown it up over here. My computer now will, there we go. You take a difference between the red and the black, and you now see we get a negative forcing. So this means you're going to have global cooling. So basically this says if you have more CO2 above a cloud layer, you get a bigger radiator, and that's going to be responsible for the cooling. That's a dramatic difference than the plus 3.15. Now, if you consider different cloud layers, you're going to get different changes in forcing, but not as dramatic as this. What's the overall effect of clouds? Probably to reduce the forcing from about 3 watts to about 2 watts per square meter. So this is an area that we are presently very strongly researching. What is the exact effect of clouds? Now let's look at the evidence. If you look at the temperature records, this temperature increased from 1900 to about 1940 by about 0.5 degrees Celsius. We don't quite know why that is. If you say that's due to greenhouse gases, you'll get a climate sensitivity of 7, which no one believes. So this temperature increase from 1900 to 1940, we don't know why that occurred. From 1940 to 1980, temperatures flat, maybe even they went down a little bit. From 1980 to 2000, we have an increase of 0.5 degree Celsius. Probably a lot of that is due to greenhouse gases. But then something remarkable happened. From 2000 to 2016, there was a pause in global warming, something known as the hiatus, and no one knows why that occurred. The point I'm trying to make is that warming, the fits and stops or pauses of this warming doesn't seem to coincide with this increasing of greenhouse gases. So there is more than just greenhouse gases responsible for these temperature warming of the Earth. Now, one thing the IPCC likes to talk about is something called the global warming potential. This gives rise to high numbers that tend to scare people. So let's look at what that is. So basically, it's an attempt to show the warming of a molecule relative to CO2. So if you take the forcing arises when you double the molecule concentration. If you take the forcing and divide by the column density, then you get something called the power. They then divide by the mass of the molecule, Mi, and then multiply this function theta that depends upon the time that you're considering for the global warming potential. Now this time, this theta function, I'm trying to struggle with my cursor so that you see it. This theta depends on this integral of this exponential function and this exponential time constant. That's the lifetime of the greenhouse gas molecule in question. So down here are some of the results. For CO2, since the global warming potential is a ratio to CO2, this power is 1. For methane, we get 31. Basically, that says if I put one methane molecule into the atmosphere, it has 31 times greater global warming effect than one additional molecule of CO2. For the case of N2O, one additional N2O molecule has 233 times the warming effect than one additional CO2 molecule. Now, if you look at the results in the last line for N2O, the global warming potentials we calculate agree quite well with the ones from the IPCC report. They get values of about 273 for a global warming potential for 20 and 100 years. In the case of methane, we are slightly below. The reason I believe is that the IPCC does not just consider methane, but when methane decomposes high in the atmosphere to produce carbon dioxide and water vapor, it also considers those products of the decomposed methane molecule. So those indirect effects are added to the direct effects of methane that we consider. Now, we didn't consider those indirect effects because we're not quite certain how the IPCC does that. Now, I don't think this global warming potential is a very useful concept. If you wake up in the morning, you don't say, honey, what's the global warming potential today to decide whether to put on a jacket. What you want to know instead is, what's the effect on warming? So we looked at the effect of these various gases on warming as follows. First of all, we assume the greenhouse gas in the coming century will continue to increase at the observed 2020 rates. We picked that time period rather than say the period 1990 to 2020, because during 2000 to 2020, methane in particular did not slow down. So that awkward situation in 1990s where methane concentration stopped or even dropped, we don't ignore, we don't consider that. So what we're trying to do here is come up with numbers that give you the highest likely warming that you can possibly get according to this global warming theory. We're going to assume that the warming in the 21st century is the same as in the 20th century, about 1 Kelvin or 1 Celsius, and that all of that warming is due to greenhouse gases. And that's probably unlikely. We'll talk about that later. Finally, we assume that the greenhouse gas warming is proportional to its forcing. So here, if we look at this table, CO2, the present concentration is about 410 parts per million. methane 1.9 parts per million, N2O 0.34 parts per million. If we then look at the rate of increase of these greenhouse gases relative to CO2, we see that methane is going up or is being added to the atmosphere about a factor of 300 times less than CO2. So we're putting about 312 CO2 molecules for each methane molecule. For N2O, we're adding about 3,125 CO2 molecules for every N2O molecule. So even though both methane and N2O are much more effective than a CO2 molecule at global warming, but because we're putting in so much more CO2, the net effect of the methane and the N2O is much less. So you basically have to take this factor of 31 for methane, divided by the 312, that's the difference in the number of the molecules that's being added to the atmosphere compared to CO2. And 31 divided by 312 is about 1/10. So the effect of the methane is about 1/10 that of CO2. For the case of N2O, 233 divided by 3125, it's a bit less than 1/10. So we get a warming of about 0.06 degrees Celsius per century. If we add those three up, we get about 1 degree centigrade per century. Now, are there any drawbacks? Well, if we were to say, let's stop the increase of N2O, which we could do by saying you're not allowed to use fertilizers, this would have a dramatic effect on crop yield. So here we plot some data we found for the United States. The vertical axis on the left is crop yield relative to 1866. You see crops of corn, wheat, barley. Yields did not really increase until about the 1950s, when you start to have great use of fertilizers. So the dashed blue curve shows the increase of nitrogen fertilizer use. Now, of course, there was a lot more going on than just using fertilizers to boost agricultural yields, better seeds, better farming techniques, etc. Nevertheless, the use of nitrogen fertilizers was very important to dramatically increasing the world food supply, basically ending famine. Now, if you look at the increase of CO2, there are some effects on vegetation. I think we all know that if you increase CO2, plants grow faster, and that's shown here by this pine tree. The left one was a pine tree grown at standard atmospheric concentration. Then they enclosed the pine tree in a bag, put in 150 parts more CO2, and 300 parts per million more CO2, 450 parts per million CO2. So you see a dramatic increase in growth. And every greenhouse grower knows that, and that's why they pump CO2 into their greenhouse. But there's another effect. If you put in more CO2, if you have more CO2 in the atmosphere, the holes in the leaf through which the plant gets the CO2, which is of course plant food, shrink in size. If they shrink in size, there is less water loss from the plants, so the plants can grow in drier areas. And that has been shown by this so-called greening of the earth, which is particularly evident on the borders of dry areas, such as the border of the Sahara. So this is analogous to having a bunch of teenagers around the dinner table. If there's a lot of food in front of them, their mouths shrink in size. Now I'd like to talk a little bit about the climate models. If you want to test the climate models, you want to say, where do we expect the warming to be most significant? And it turns out that is not at the surface, but it is at the tropopause. So in this upper diagram, what we show here is the change in temperature versus altitude. When air is very cold, there is very little water in it, and the temperature decreases by about 10 degrees Celsius per kilometer, or exactly 9.8 Celsius per kilometer. As you warm the air, you get more water vapor, and then the temperature changes a lot less, about 6.5 degrees Celsius per kilometer. Now, if you take a package of air at the surface and look at, say, the difference between the blue and the red curve, at the surface, we get a temperature change, which is much less than the temperature change at 11 kilometers, which is the difference between the blue and the red curve at this altitude of 11 kilometers. So the theory predicts the greatest warming will occur at the tropopause. So let's see how well the models do. And that's shown down below. So the dashed white line, that's the observed warming at the tropopause, about 0.17 Celsius per decade. The black dash, that's the average of 39 different models, about 0.4 Celsius per decade, more than double what's observed. Red are the individual GCM products, and we see all of these models greatly exaggerate the warming. Now, that is not because these are evil people. It's just a difficult problem to do. The uncertainty, they think, is largely due to clouds. I'd like to briefly discuss what's going on with the polar ice cap. If you increase the temperature, you would expect the ice to go down, and that's indeed what's observed in the Arctic. In fact, this summer minimum ice extent has been going down very sharply since 1979. If you extrapolate that red line to the zero axis, we predict no summer ice in 2077. But if you look at the data for the last 16 years and fit a dashed red line to that September ice, then it turns out that line has a flat slope and you don't get zero ice until about 4729. The Antarctic has been slowly, the ice extent has been slowly increasing. Only the peninsula, which juts up towards South America, seems to have a warming in recent years. Nevertheless, if you have warming temperatures, you get less ice, there are dramatic effects. And this quote below is, I think, quite significant. The Arctic is not recognizable as a region of previous 50 years. Glaciers have been replaced by mounds of earth and stones. Great shoals of fish have disappeared and the seal population has diminished. And this is from the reference George Ift in the Monthly Weather Review, page 589. The year of that quote is 1922. Now, besides the polar and Antarctic ice caps, we hear a lot about glaciers on land shrinking. And this is very evident when you take a trip to Alaska. There's a place called Glacier Bay, and my sister-in-law went there recently, and you get some very nice pictures showing how the glaciers are shrinking. The first cruise ship, captained by Mr. Vancouver, came in the late 1700s, and at that time, the ice went all the way to the Pacific Ocean. 20 years later, it had retreated to this level. Another 50 years, 1845, it retreated more, etc. So we see a dramatic retreat of over 50 kilometers during the 1800s and in the period before 1950. And no one seriously says that retreat is due to greenhouse gases. So there's a lot of warming going on here that is not due to greenhouse gases. It's probably this end of this little ice age that we experienced in the last few hundred years. So conclusions. First of all, increasing greenhouse gases do cause some warming. If we extrapolate the warming to the 21st century, we get the following results. For CO2, we get a warming of about 0.85 Celsius per century, methane 0.085, N2O 0.064. I'm in Ireland, and so if we consider the Irish contribution of these greenhouse gases, turns out the Irish warming is very small. And of course, if you're interested in agriculture, according to the Ireland climate people, agriculture is responsible for about 1/3 of the CO2 equivalent. CO2 equivalent means what's the warming that you get from these other gases. So then you'd have to multiply these green figures by a fraction of 1/3. So we see the Irish fraction is just minuscule. We won't be able to measure that. So if the people go to demonstrate to the Irish Prime Minister to outlaw greenhouse gases, that is going to have a negligible effect on climate. To be effective, you really want to go and demonstrate in Tiananmen Square. And the leader of China and also the leader of India, these developing countries that are producing a lot of greenhouse gases because they want to generate electricity for their people, increase the standard of living, et cetera, are going to say, do you really expect us to cut our development if the effect of, say, increasing nitrous oxide is less than 1/10 of a degree per century? Absolutely not. And similarly for methane, you can see very little effect on world temperatures. The evidence, the Earth has warmed by about +1 Celsius since 1850, but the global climate models have a poor prediction record. There's been a slight ice increase in the Antarctic, a reduction in the Arctic since '79, but the minimum Arctic ice extent seems to have stabilized since 2007. There's been a dramatic retreat of glaciers before 1950, such as in Alaska. No one seriously thinks that's due to greenhouse gases, but probably a warming of the Earth following the end of the Little Ice Age. So our conclusion is that the Earth is not facing a climate Armageddon in the next 10 years, as stated by the UN Secretary General. And we ought to be careful. If we outlaw or severely restrict fertilizer use, you could endanger the world food supply. And if countries such as Ireland, Holland, the United States pull land out of agricultural use, that fertile land has to be replaced by land, say, in a place like the Amazon. And if you cut down the Amazon rainforest, what remains is relatively infertile soil. So you have to cut down a much greater area of Amazonian rainforest to replace the agricultural benefits of this fertile land, say in Ireland, Holland, North America. So one has to be very careful about unintended negative consequences to one's action. Thank you for your attention.